Let ABC be a scaling triangle with incenter I. The incircle of ABC touches BC, CA, and AB at points D, E, and F, respectively. Let P be the foot of the altitude from D to EF, and let M be the midpoint of BC. The rays AP and IP intersect the circumcircle of triangle ABC at points G and Q, respectively. Show that the incenter of triangle GQM coincides with D here. So we wish to show that the incenter of the red triangle is just this point D here. So how do we get started? Well, we have this random foot of the altitude here, and this incenter here. So we can recall the properties from my last video. Go ahead and watch that if you haven't already. I'm linking it in the description. But basically, if you draw in the circumcircle of triangle AEF, which is shown over here now, then if you let then Q lies on the circumcircle of AEIF. And we can actually define Q in that way and eliminate this line IP entirely. So we now know that Q is just the point identified in the last video, but the real problem is this point G. So now let's go ahead and see how we can interpret this condition. In order for this to be true, we must see that QD bisects angle GQM. So something like that. However, from the last video, we also know that QD bisects angle BQC. So we can go ahead and draw those in. So there we go. So if we wanted to show that these two angles were equal, then given these two angles were equal, we have to show that angle BQG is equal to angle MQC. And now we notice that the midpoint M is thrown in here, and so are these isogonal lines. So it suffices to show that QG is a symmedian. So QG is symmedian. And by harmonic quadrilateral properties, this amounts to showing that the quadrilateral BQCG is harmonic, or equivalently that BC then QG is equal to -1. So how do we get started on proving this? Well, the only obvious way that the point G is defined here is as an intersection of AP with a circumcircle. And P is on line EF, so it makes sense to project this thing from A onto EF. So let's go ahead and draw EF. Then we draw in the line AQ. And suppose it intersects at a point X. Then it suffices to show that X, the bundle X, P, F, E is equal to -1. And now this is where things get interesting, because we now have this line AQ intersects at X, and we want to show a harmonic bundle is true. And this means that we can just get rid of the point a whole lot of points. Now I've cleaned up our diagram here, so it suffices to show that this cross ratio here is -1. So our main trouble spot here is the point P, because we don't really know that many lines that it lies on. So it lies on two lines that are relatively clean here, and they're both in the diagram. The first one is a line through D perpendicular to EF, and the second one is a line QI itself. If we try projecting through D, then things will get a bit too complicated, because it will involve things with the line GX, and we don't really know things about that. So let's try projecting through Q. And doing so, if we project through Q onto the circumcircle of AEF, we end up getting, so X gets sent to the point A, P gets sent to the point I, and then F and E are fixed, we must show that this is -1. But this is clearly true because AEF is isosceles and I is the point diametrically opposite A on the circumcircle. So this quadrilateral here is harmonic, and then projecting through Q gives that this cross ratio here is -1, and then finally projecting through A again, we get that this thing here, if we have this point G here, then BCQG is -1. Now we are back at our original diagram here, knowing that this is true because we just proved it. And earlier we said that this implies that QD bisects angle GQM. Now we just need to find one other angle bisector, and that will show that D is the incenter. So using MD bisecting angle QMG doesn't seem the nicest because angle QMB doesn't seem to work well. So let's try showing that GD bisects angle QGM. So, and given that this quadrilateral here is harmonic, this implies that BQ over QC is equal to BG over GC. And by the angle bisector theorem, since QD bisects angle BQC, this is equal to BD over DC. And this implies, again by the converse of the angle bisector theorem, that GD bisects angle BGC. So we have this line here and this line here. So once again, by our orthogonal line thing, we must show that this angle here is equal to this, this angle here is equal to this angle here. But we know that this quadrilateral is once again harmonic. We keep using this fact, and therefore GQ is the submedian of the triangle. And this implies that these two angles are equal, and since angle BGD is equal to angle CGD, that implies that these two angles in here are equal. And since we also know that these two angles are equal, that implies that D is the incenter. So let's recap what we did. So we first showed that the quadrilateral is harmonic by using a few projections. We first projected from A onto EF, then from Q onto the circle, and concluded. Then we used the angle bisector theorem to show that GD bisects angle BGC and QD bisects angle BQC. And we already know that QD bisects angle BQC because of the properties of this point Q stated in the last video. And therefore, QD bisects angle GQM and GD bisects angle QGM. And this implies that the incenter of GQM is D. And this solves our problem. So thank you so much for watching this video. Please subscribe if you'd like to see more.